Hi again. Today I want to continue with our exploration of homologous series and groups of hydrocarbons. Today we're going to look at unsaturated hydrocarbons, the alkenes and the alkyne family. Let's begin where we left off last day by a look at the alkane family. I have here a molecule of ethane, etha, again 2 carbon, ane telling me a member of the alkane family. The presence of the single bond indicates that the substance is full of hydrogen. It's holding as many as it can, in this case 6 hydrogens. You might recall that the alkane family is one of the more unreactive families in the organic chemistry, primarily due to the strong carbon-carbon bond. That's called a sigma bond, a single bond represented by an overlap of ends of orbitals. And you might recall that these substances undergo combustion and substitution reactions. And now we'll look at our unsaturated families. First, the alkene family, recognized by the finishing or the suffix ene on the end, or ene. And also the alkyne family. Again, the suffix yne on the end tells me the presence of a triple bond. And as mentioned earlier, these are unsaturated in that they could hold more hydrogens. In the case of ethene, it could hold 2 more hydrogens, and ethyne could hold 4 more. These seem to be somewhat more reactive than the alkane family, primarily due to the presence of what's called a weaker pi bond. The double bond is made of 2 types of bonds, a very strong sigma bond and a weaker pi bond. An exploration of bond enthalpy shows us how this works. If I look at the carbon-carbon single bond, I'll see that its bond strength is 346 kilojoules. If I look at a carbon-carbon double bond, it's 614. That's less than double the 346. In fact, it's only an increase of 268. That 268 is associated with my weaker pi bond. So when this substance reacts, it tends to be that weaker pi bond where the attack or the reaction takes place. These substances also undergo combustion reactions, but not substitution. They undergo what are called addition reactions. Let's look a little bit at how these substances are named. So I'll try to name this compound I have here on the left. I'm going to refer back to some of the rules we had earlier for the alkane family. I'm going to start by identifying the longest continuous chain, but in addition I have to take into account the presence of the double bond. So I must always number the chain such that it includes the double bond. This is a 5 carbon chain, pentane, but the presence of the double bond means I should change the name to pentene. I number the chain such that I begin my numbering at the end closest to the double bond, which in this case has already happened. I'm going to identify my side groups and in addition the location of multiple bonds. So I have a methyl group on carbon number 4, and between 2 and 3 I have a double bond. So this is a 2-pentene. I'm going to group these names together if there's any common branches, and in this case there aren't any. So I'm going to bring it down now, 4-methyl 2-pentene. Now this tends to be a way we name chemicals in North America, and it may differ slightly from what's in your textbook. A more European technique is to replace 2-pentene with pent-2-ene, and it's a more accepted method in naming organic chemicals.
Reactions of alkenes. They tend to undergo what's called electrophilic addition. First of all, what's meant by an electrophile? An electrophile are a group of substances that like electrons. These would include things that have positive charges like cations or polar compounds that have slightly positive regions within them. The 3 electrophiles we're going to cover include electrophilic addition of a halogen halide, and water. First off, let's look at the addition of a halogen. In my case, I'm going to use bromine. So here we have our electron-rich region, and the bromine is attracted to it. It can create what we call an induced temporary dipole. If that region is highly negative, then the bromine closest to it would develop a slightly positive charge and therefore be attracted towards it. What happens in our reaction is we can imagine the double bond breaking, so we have only a single bond existing between our carbons. Hence, each carbon is now capable of taking on a new partner. The bromine splits, and 1 bromine moves to each of the vacant areas, resulting in the formation of 1,2-dibromoethane. Here we can see the overall reaction. Now this reaction with bromine is a particularly important one for identifying whether or not a substance has multiple bonds. It's called the bromine test for unsaturated hydrocarbons. We begin with aqueous bromine, where we have liquid bromine dissolved in water. We can add that to our test samples, which we suspect have multiple bonds in them. If the sample contains multiple bonds, we'll find that the color will become less intense. It might even, in fact, become colorless. If the color persists, then we don't have multiple bonds. Now let's look at the addition of a halogen halide. In my case, I'm going to use hydrogen bromide. There's my electron-rich region within this 4-carbon molecule. And hydrogen bromide is a permanent dipole, so the hydrogen, being slightly positive, would be attracted to this location. As before, we can view the carbon-carbon double bond springing open, creating 2 openings. And in this case, hydrogen would move to the one site, bromine to the other. My resulting compound would be called 2-bromobutane. And here's the overall equation for it. Lastly, let's look at the addition of water. This is sometimes referred to as hydration. I'll use the same molecule as above, 2-butene. And here's my water molecule, and again, it's slightly polar, the hydrogens being positive, the oxygen negative, and my carbon-rich region. That carbon-rich region springs open to create 2 openings. Now in this case, watch carefully how it breaks. One of the hydrogens breaks off and goes to one of the carbons, and the OH to the remaining fragment. So as a result, we end up producing an alcohol. In this case, butan-2-ol. For those of you taking higher level chemistry, be sure to watch the next video, which presents the mechanism for electrophilic addition. Give us a like if you found that useful.